When we start looking at simplifying radicals, we'll begin with, well, there's certain vocabulary that you need to be familiar with um, because it will be used regularly. So just to clear up any confusion, numbers that we multiply to get another number, those numbers are called factors. A number that can be divided only by itself or one is a prime number. The little number that tells us what type of root. This is the small number just outside a radical, and this is called the index. And a number under the radical here. Sometimes there are also variables under the radical. But this, whatever is inside, that's called the radicand. If you don't see a number in the index, it's a 2. The reason for that is we know this is a square root, and we know this is inverse of a quadratic. And so these are related. So when this is blank, we call that square root, and the index then is a 2. I'm going to go ahead and break down these numbers into their prime factors. 42. 42 is 6 times 7. 6 is 2 times 3. When you break down a number into the factors to where there's nothing, there's no way to factor them further because now they're prime, they can only be divided by themselves or 1, then this is a prime factor tree. I can do this with 120 also. 120 is 10 times 12. 10 is 2 times 5. And 12 is 2 times 6. 6 is 2 times 3. Oh, weirdo looking 3. Goodness me. There. Oh, yes. So much nicer. So now all of these on the bottom are primes. Also, I have 225 here. 225 is 25 times 9. Sorry. And 25 is a perfect square. It's 5 times 5. And 9 is a perfect square. It's 3 times 3. So this is how we'll factor so that we could simplify our radicals. Next, we have steps for simplifying radicals. To make this as few steps as possible, I would say write the largest factors of the radicand. So break it down into big chunks. Expand when we're factoring, we say we're expanding. Expand to primes if applicable. So that's like the factor trees we just drew. Circle groups based on the index. So what I mean by this is for a square root, I would need sets of 2. A cube root would need sets of 3. A fourth root would need sets of 4. The index is what tells you how many matching factors would comprise a set. Pull out one term for each circled group. Everything else that you didn't circle stays inside the radical. It stays under the radical. Multiply everything outside together. And multiply everything inside together. One thing to make a note of here is that when we're simplifying radicals, the radicand must be positive. So I'll write simplified radicals have positive radicands. Here I have 4 examples to work with you. This is a square root, so my index is 2. So I'll need sets of 2 matching factors to reduce. 50 is 5 times 10. 10 is 5 times 2. So here I have a set of 2 matching factors. They're 5s. So I can pull out 1 5 to represent the group. And this 2 does not have a pair, so it has to stay under the radical. And this is simplified. With 64, I'll need sets of 4 matching factors. 64 is 8 times 8. 8 is a perfect cube. 2 times 2 times 2. Okay, so I need a set of 4 matching factors. So here I'll pull these 4, and then these 2. I don't have enough other 2's to be able to simplify out another group. So I'll have 1, 2 to represent this group of 4, and remaining in the radical, which is a fourth root, I'll have 2 times 2. I'll multiply those back together. Here's my next example. I have a square root again. We can break down 20. It's 4 times 5. 4 is 2 times 2. It's a perfect square. So here I have a set of 2 2's and a 5. The 5 will have to stay behind. X to the third is x times itself 3 times. So I can find another set of 2 x's, and this x will have to remain inside the radical. I started with a 2 outside. So I still have the 2 that's outside, and I bring out a 2 to represent this group, and an x to represent the second group. And inside my square root, I have 5 times x. We'll multiply together everything outside, which gives us 4x. And we'll multiply these together inside, which is 5x. That one's simplified. Last one. I have a cube root. I also have a negative radicand. And simplified radicands have positive, or simplified radicals have positive radicands. So I'll have to find a way to pull the negative out. 81 is negative 9 times 9. Negative 9 is 3 times negative 3. I need to make sure this negative comes out. So I can write 9 as negative 3 times negative 3, because negative times negative is positive. And if I write it that way, then I'll have a set of 3 matching, or negative 3's. So I can pull out this group. X to the 5th is x to the 3rd times x squared. With exponents, you add the exponents together. X to the 3rd is 3 x's multiplied together. X squared is 2 x's multiplied together. My index is 3. So here I can reduce the x from the radical. Y to the 3rd is y times itself 3 times. So I can make a group of 3 y's as well. What stayed behind is a positive 3 and an x squared. Those will remain under the radical. Simplified, I have negative 3 x y. It's strange. Cube root 3x squared. Okay, you have practice to do. It's a maze. Let me know if you need any help.